All right. Hi, everybody. Thanks for the invitation. It's a great pleasure to be here. Right. So I'm going to tell you today about accidental symmetries near extreme black hole horizons, extreme and near extreme black hole horizons. So what do we care about extreme and near extreme black hole horizons? Well, they're observationally irrelevant. They seem to appear up there in the sky when the black holes are Kerr, and near extremality they are ADS2-like. But the prototypical example that everybody knows here is that the Bertotti-Robinson universe is ADS2 cross S2 is just the near horizon of extreme Reisner Nordstrom. So most of the talk I will explain in this context, but we've done calculations that are now work for Kerr as well. So let me quickly remind you. You take the near horizon limit of those extreme and near extreme black holes. This ADS2 arises. Why? Well, it's actually a theorem in a very wide class of theories in many dimensions with minimal assumptions, and it basically consists of two things. The kinematics of saying that you have an extremal horizon implies that you have a scaling symmetry. But then the Einstein equation is the thing that adds and completes the algebra to SL2. And once SL2 arises, you have to have ADS2. So that's why this is so ubiquitous. But what I want you to take from this slide is that while these are approximations of the near horizon of extreme and near extreme black holes, they are also exact solutions of those equations, the same equations of motion. They're also exact solutions. So you could think about living in such a universe, let's say the Bertotti-Robinson universe, and asking about its perturbations. And it was already known back in the days from some of our most illustrious colleagues that back reaction in this type of context is kind of problematic. It's a bit strange and weird. And we can illustrate this from the gravitational point of view if we think about 4D gravitational physics as follows. So suppose you have a little bit of perturbation in this Bertotti-Robinson universe, for example. Let's say a scalar field phi, which you put on there, and you let it back react on the geometry. Is there a nonlinear completion of this situation to a nonlinear solution of Einstein-Maxwell scalar? And the answer is no, if you insist that this solution is still asymptotically ADS2. So the answer is no to that question, and that's what it meant, that ADS2 has to fragment, that there's no dynamics within asymptotically ADS2 spacetimes, etc. But of course, I mean, especially when we're talking about the black holes out there in the sky, something has to happen. If this is a near horizon approximation of an asymptotically flat region and there's a little bit of perturbation there, what happens? Back reaction somehow must make sense. And it does make sense when this ADS2 is actually connected to the asymptotically flat region. So if you consider the back reaction problem in asymptotically flat spacetimes, it does make sense, perfect sense. So this was realized, I guess, more recently, especially with the work in JT gravity. But of course, you would also like to make some calculations. And in this very nice paper, where they do some numerics, they actually study precisely this problem. They put in a scalar of order epsilon on extreme Reisner Nordstrom in the near horizon region, and they nonlinearly find the endpoint of that. And they do indeed find what you would expect, that what this does is it perturbs the black hole a little bit away from extremality and produces a near extremal Reisner Nordstrom with charge to mass ratio controlled by the size of that perturbation you put in. So if you do this problem in asymptotically flat spacetime, it does make perfect sense. So I want to quickly explain in this 4D type of language, how does the connection of ADS2 with another region outside help with this type of thing, and what are the correct boundary conditions, what's going on, etc.
Is it a reason why you're thinking of it as like decreasing the charge?
This formula?
Yeah. Instead of saying like that I have some amount of charge and I increase the mass of the
No, don't read too deep into that. The reason I wrote it this because it's convenient to write it this way. I mean, all this is saying is that you start exactly extremal, you add a little bit of energy, it becomes near extremal by increasing the energy.
Right, but the mass is big, so I would have increased the mass of the black hole.
I agree. I agree, but yeah, don't read too much into this. The difference between charge to mass, the only thing that this tells you is what power, what's the important power there. But yes, the difference is the thing that is the extra energy. Okay, so this is the charge to mass ratio of the final near extremal black hole, and it's epsilon the 1/2 away from being 1. Okay, so for this first part, I want to quickly introduce this concept of anabasis. For those of you who are not Greek or don't have a Greek origin, anabasis is a Greek word which means ascent to some kind of hill, some kind of low gravitational energy potential region, something like that. So ascending something. So this is the concept of anabasis, and I call anabasis the back reaction that destroys ADS2 boundary and builds this asymptotically flat region of extreme and near extreme black holes. This process of back reaction that destroys ADS2 boundary conditions is what I call anabasis. So let me review this real quick. So suppose you are such a Bertozzi-Robinson observer. You live in this universe. The universe is asymptotically ADS2 cross S2. You study perturbations of it, and let's just study spherically symmetric perturbations of a magnetically charged version. So this is your background. You study spherically symmetric perturbations, and they are fully characterized by this gauge invariant quantity. Because it's spherical symmetry, this is not a propagating perturbation. All of the spherically symmetric perturbations are just 4 parameters, phi 0, A, B, and C. And they're all physical because this H theta theta component is gauge invariant. So what do these 4 parameters do? Well, you recognize what phi 0 does. It sets the scale of your universe. So if you change this M to M plus delta M, phi 0 measures this delta M difference. So you understand what that is. That's a parameter of your universe. What are the ABCs doing, though? The ABCs, let's collect them in this field phi. Let's call this solution phi. And let's see what they're doing. Well, they're breaking, first of all, they're breaking the SL2 isometries of your background. They know none of these solutions respects the SL2 isometries. So these SL2 transformations will rotate this ABC solution to another one. However, it will not rotate it completely arbitrarily. There is an invariant quantity, this SL2 invariant Casimir, a quadratic of ABCs, which has to stay invariant. So if you apply SL2 transformations, isometries of your background, you can rotate your ABC solutions around. And let's make a choice. Let's say that when mu is equal to 0, you're going to rotate away B and C and set the canonical solution to be A times R, let's say 2R here. And if mu is positive, let's say you're going to make the choice to rotate away A and C such that phi now is square root of mu times RT. All right. Notice that these SL2 breaking solutions, they're not asymptotical ADS2. They're growing linearly with R, near ADS2 boundary. ADS2 boundary in these coordinates is at R equals infinity. So, U negative, I don't know how to interpret that. It might have something to do with having another asymptotic region, maybe wormholes, something like that. But that would require more study. Yeah, so I will assume that mu is positive or 0. All right. So why? Why there are these two cases? Because there are two ways to do anabasis of BR, of Bertozzi-Robinson. So Bertozzi-Robinson can arise from the near horizon of this Reisner-Nordstrom black hole of charge Q and mass M in two different ways. So the first way, the first limit here, is to set Q equal to M from the start and write the one parameter family of coordinate transformations like this, which puts the horizon at R equals to 0. But there is a parameter lambda in these coordinate transformations, which you then send to 0. Then there is a second limit, which you can do as follows. You can start with the Reisner-Nordstrom, which has this charge to mass ratio, so not exactly 0 initially. Do also a similar coordinate transformation, one parameter lambda, and send that to 0. So now the horizon is going to be map onto rho equal to 0. And these two yield the two different mu's. So in the first way of taking the limit, you will produce your Bertozzi-Robinson universe at order 1, leading order, in Poincaré coordinates like here. And then by definition, if you look at what's the first order correction of this limit, you will produce one of those perturbative solutions of around Bertozzi-Robinson. And what you get in terms of the theta component is this 2R here. So what this tells you is that the 2R solution, which is the canonical version of any mu equal to 0 solution, up to SL2 transformations, is just a solution which I call a Poincaré anabasis solution, because what it does is, if you think of the limit in the opposite direction, is it begins to build the asymptotic region of the exactly extreme Reisner-Nordstrom starting from Bertozzi-Robinson. So the lesson is the nonlinear solution obtained from any mu equal to 0 perturbation of ADS2 cross S2, when you take into account back reaction fully in Einstein-Maxwell theory, is an exactly extreme Reisner-Nordstrom black hole. How about the limit number 2? So limit number 2, if you do exactly the same exercise, but with the different charge to mass ratio to begin with, and the different coordinates, at order 1 you get this. This is still Bertozzi-Robinson, but written in Rindler coordinates. And at order 1, you get a perturbative solution around this background here, which is given by this equation over here. So I'm saying this is still Bertotti-Robinson, so let's put it back into Poincare coordinates, both it and the linear solution around it. And here's the transformation which will do it for you. So tau and rho goes to T and R. Here's a Penrose diagram. In TR coordinates cover the big wedge here. Tau rho coordinates cover the small wedge here. If you do this, the backgrounds go to each other. So now you have Poincare coordinates for the background. What does the perturbative solution from limit 2 map to? It maps to this minus 2 kappa times RT. So it maps to a positive mu solution. So limit number 2 produces an anabasis solution, which you might call the Rindler anabasis solution. And it's a positive mu solution. So we learned that those positive mu solutions, up to SL2 transformations, remember they can all be mapped to this one basically. What we learn is that those positive mu solutions, when you take back reaction fully into account in Einstein-Maxwell theory, what they will do if you start off Bertotti-Robinson is they will build for you an asymptotically flat region that's associated with a Rice-Norton black hole with non-zero deviation from extremality given by this square root here. So that's anabasis. So let's summarize real quick what's anabasis. It's back reaction that destroys the ADS2 boundary and builds an asymptotically flat region of extreme and near extreme black holes. All right. I guess a few remarks. It's natural to ask, what about JT gravity? I'm talking in 4D language only, but it's natural to ask what about JT gravity. But all of these quantities, of course, make an appearance in the JT formulation of higher dimensional gravity down, in the JT reduction of higher dimensional gravity down to 2D. So the thing I was calling phi actually gets identified with the JT dilaton and satisfies this dilaton equation in JT theory on ADS2. The thing I was calling nu, the SL2 invariant, is an ADM mass of 2D black holes you can define in these 2D theories of gravity. And the thing that many people call nearly ADS2 geometries are precisely the geometries you can make by adding this type of anabasis perturbation to your exact ADS2, and therefore now having the SL2 broken appropriately such that you're maintaining connection with an exterior region. So this is what you would call nearly ADS2 solution in this context. So it's basically the background, the exact ADS2 thing, plus the anabasis perturbations. All right. And I guess if you care a lot about horography, you would also want to know what is the dual of doing anabasis in ADS-CFT type of language. Well, that's a little trickier. I'm not 100% sure. I mean, the basic intuition is the following. What it is doing is it's following inverse RG flow from the IR to UV along an irrelevant deformation, but in such a way that you don't respect the ADS boundary conditions. That's not something we very often do in ADS-CFT language for good reasons, but it does happen. In fact, string theory was discovered, holography was discovered this way, right, from string theory going in the opposite direction. It's a hard question if you start from the IR. It's a hard question to go up because you don't know how, what deformation to follow that's solvable. The only example I know where this has been done successfully is for ADS3, not ADS2. There are these TT bar deformations, single trace version of them, which people understand that they start with an ADS3, they follow it, they can solve it, and they produce an asymptotically flat linear dilaton type of solution. So this is an example of how this type of anabasis or inverse RG flow can work. Now, what it is for ADS2, though, not so clear. I don't fully understand how to think about RG in 2D. Yeah.
Can you say that this is analogous to, let's take NS5 brains, take a near horizon limit, where the solution becomes extreme times the linear dilaton. So the analysis in that case would be to start with this, which has an exact description, and see how we can restore back the one.
That's right, yeah. Yeah, that's the intuition, indeed. Right. If you know the parent theory, of course. String theory. Holography was discovered this way. If you know the string theory, you can go down. Yeah, you don't know what's up there, and which deformation you should follow in such a way that it is solvable, etc. And you discover the physics that's asymptotically flat. That's difficult. Right. Yeah.
But also, like in the ADS2 case, right? So
that's also another setup where this can be understood. I suppose if it's going from asymptote Galeidis 2 to asymptote Galeidis 3, that there's more control in there. That's also a good point. Yeah. Yeah.
That's what a little bit of what I think what Professor collaborator did is look at the near horizon of NS5F1, and basically you add the one that you get out of the throat, and you go to the linear relation of the metal.
Right. Yeah. But we want that type of understanding for something that starts with ADS2, and so yeah, that's different from what Kudosov and friends have. There's less control. Okay. I mean, I don't even fully understand what it means to say that you're doing you're adding an irrelevant deformation of, I don't know, conformal quantum mechanics, some CFT1 type thing. Yeah. In one dimension, what does RG mean? This is a tricky question. Okay. Good. So that was analysis, but the main part of my talk is about this accidental symmetry that we discovered. So there is an accidental symmetry, which is, what is an accidental symmetry? We define it as a coordinate transformation which acts on perturbative solutions of the Einstein equation, so solutions to the linearized Einstein equation, around extreme and near extreme horizons. So there are some coordinate transformations which can map various solutions of these linearized Einstein equations around extreme horizons. So let's be a little schematic and describe what these are. So imagine that you have this, which is a schematic for the linearized Einstein equation, which you build out of a background geometry G bar, and you find solutions for the perturbations H. So you want this equation to be satisfied when there's a background, let's say the Bertozzi-Robinson universe, ADS2 equals S2. There are metric perturbations of it. Let's call them H. It could be one of those ABC solutions, the phi thing. And you're trying to solve this equation. Now, do a coordinate transformation. This is a perfectly covariant equation of motion. So if you do an arbitrary coordinate transformation like this for an arbitrary vector field C, you will transform both the background, G, that's a tensor, and the perturbation H, that's another tensor, in such a way that for arbitrary lambda and C, this equation is still valid. This is just general covariance. All right, now expand this in lambda. So make a linearized diffeo, so an infinitesimal diffeo. At 0th order, you have this term. At first order, you get two terms. You get a term when you expand H, and you get another term when you expand G. If you start with a solution of this original equation, then this is 0, and therefore the sum of the other two has to be 0. So no matter what diffeo you did, the sum of these two terms always has to be equal to 0 if you're transforming an initial solution. But let's think about what these two terms actually mean. The first term says, hold the perturbation fixed, but do an infinitesimal diffeo on the background. The second term says, do the opposite. Hold the background fixed, but transform the perturbation, transform the solution. The sum of them is always 0, but what if we impose the requirement that we want each of them individually to vanish? So suppose I want to insist that the second term vanishes by itself. What does that mean? That means I want to be able to find a transformation of various perturbative solutions around the same background in such a way that this equation is satisfied. Should there even be such solutions? Should there be diffeos I can do just on the perturbation and get a solution? Well, if you think a little bit about it, you know that there should be at least one type of such diffeos if there are isometries of the background. If the background has isometries, symmetries, then I can act with those isometries, and my background doesn't transform. So the transformed G bar is the same as G0. Well, in that case, this is just the original thing. This is just this, and it has to be 0 by general covariance. So if there are any isometries of the background, this equation has to be satisfied, and it always will be. Now, anything more than that, we call an accidental symmetry. Anything more than that doesn't have a simple explanation like that, and it would need explanation if it exists. So any other solution, any other transformation that you can do, which transforms various solutions H of this linearized Einstein equation, is an accidental symmetry by our definition. So let's run this experiment on the simplest case where the background is just Bertozzi-Robinson. The perturbation is, let's say, one of those mu = 0 solutions, this one. And we're solving the linearized Einstein-Maxwell equations in electrovacuum in spherical symmetry. Well, if you actually solve this equation for all of those vector fields C, you find that the solutions take this form. These are all of the solutions. For an epsilon of t, which is an arbitrary cubic polynomial of t. So what is there? Well, E0, E1, E1, E plus minus 1, and E0 are the things that give you the SL2 killing vectors of ADS2. So you see here, what we said before, that any killing vectors will have to arise in this exercise, and they do. But there is a fourth solution. There is this T cubed mode. It corresponds to this vector field. And so that vector field is an accidental symmetry. It's a non-trivial transformation you can do on a mu equal to 0 solution and produce another solution of the same linearized Einstein equation. Now you will ask, what does this accidental symmetry do? What does psi minus 2 do? Well, what it does is it turns on mu. So remember, in the first part of the talk, I told you that if you act with SL2s, mu remains invariant. So those will never change mu. But this one could, and indeed it does. So what the accidental symmetry does is it transforms your mu equal to 0 solution to a mu positive solution in that case, if you put a coefficient E minus 2 here, which is negative. So what accidental symmetries do, even in this simplest of all contexts, just electrovacuum spherically symmetric, is they allow you to move between SL2 orbits. They enlarge the space of possible mappings among solutions of this linearized Einstein equation to go beyond SL2 and basically explore the entire set of available solutions. All right. Now you might ask, why do they call this psi minus 2? Because in writing it this way, it's very suggestive that you might expand this epsilon of t into arbitrary polynomials. And so you might ask, what does psi minus 3, psi minus 4, etc., what do all of these guys do? Well, these guys produce perturbations that now move off shell. They no longer produce perturbations which will solve the classical linearized Einstein equation. They move off shell, but they have the nice feature that they generate the Virasoro algebra. So if you consider all of the modes like that, with C minus 3, minus 4, etc., you will not be satisfying the Einstein equation anymore across the boundary, but you will have off-shell modes which are generated by Virasoro transformations of ADS2. So they are basically asymptotic symmetries. So what we learn here is that the accidental symmetry we found, together with the isometries of the background, neatly fit into the asymptotic symmetries of ADS2, the known asymptotic symmetries of ADS2. Let me make this a little bit more precise in the context of the JT theory of gravity. So suppose now you're doing this 2D theory of gravity, which approximates very well, which describes very well these dynamics in the spherical symmetric sector, at least, of black holes near extremality. What are the large diffeos of ADS2? So in Fefferman-Graham gauge, they are these guys. So you can see here that near the boundary, what this is doing is it's reparameterizing the boundary time. Remember, the boundary is in R equals infinity here in these coordinates. If you apply this large diffeo on the Poincare, let's say, background, you produce this as far as the geometry goes, and you make an original ABC solution transformed to this type of dilaton. Now this is the dilaton of the JT theory, where phi naught, the source, is given by this equation here. So if you transform an original ABC solution via these large diffeos, you make such a phi naught, and such a phi naught trivially satisfies this Schwarzian equation of motion. This is an identity. If I actually plug in this expression here and compute all the derivatives, it will be 0. All right, so there's nothing to solve here. I wouldn't call this even an equation of motion. But these are the large diffeos. Why am I saying that putting the large diffeos on shell is to transform them into accidental symmetries? Well, the reason I'm saying that is because the way to turn this into an equation for f of t, for the large diffeos, is to consider that, say you started with an original solution that had phi equals to 2r, so phi naught was constant. You do this large diffeo, but you pull it back, and you still insist that phi naught after the transformation is still a constant. So this is a new boundary condition. It changes the situation. And what it ensures is that you can still, basically what it ensures is that you can still glue into an asymptotically flat region that is a Reissner-Nordstrom region. So if you insist on that type of requirement, that phi naught, even after the transformation here, has to be constant, well, then you might find solutions that you might find constraints on your diffeos, on what f of t you can do. And indeed, if you set phi naught constant in this equation, the Schwarzian equation, it turns into an equation for f of t. if you consider only linearized diffeos, so f of t is t plus epsilon of t, this equation is just these 4 derivatives of epsilon, and it has the 4 solutions that that we have already seen, the 3 things that are associated with the SL2 isometries, and the 4th one, which is the accidental symmetry. All right. Now, on to something else. So far, I've been discussing only solutions of the electrovacuum Einstein-Maxwell equations within spherical symmetry. And so the only interesting thing I was finding is, because of Birkhoff's theorem, is this one accidental symmetry xi minus 2, which all it can do is it can add a little bit of energy, just adding a charge to the black hole. Can you have accidental symmetries do something more interesting? Turn on dynamics, turn on propagating degrees of freedom. You can. So the simplest way to do it is to not go away from spherical symmetry, not go away from Reissner-Nordström, stay here, but add, say, scalar matter. Add just a Klein-Gordon field that solves this equation here. And the most general solution for this Klein-Gordon field is, the superposition of ingoing and outgoing waves of ADS2. This type of, the most general solution like this, these are now propagating scalar waves, can actually all be generated. So they can all be generated by a diffeo, which you can use to act on the vacuum anabasis perturbation. So suppose you start with h of 0, which was just the 2R solution, and you want to act with an accidental symmetry, a diffeo, which will turn this solution into a solution that solves this linearized Einstein equation, with the source here being the Klein-Gordon source associated with this scalar field. Well, you can do that. So here's the diffeo you need to do. So this is an accidental symmetry that will turn on any desired propagating scalar wave on top of ADS2, starting from the vacuum anabasis perturbation. So that makes accidental symmetries much more powerful, and they give them more content than just adding charges, which is what you might have thought about when I advertised them as asymptotic symmetries put on shell. All right, but we wanted to generalize this for the rotating black holes, those black holes that are out there in the sky, which have a near horizon which is NEC rather than just ADS2 cross S2. And doing that required us to think about it again, because it was hard to do the old way. So we devised a new method. Let me quickly explain the method. So imagine, we will explain it on Reissner-Nordström before we apply it on NEC. So imagine that you have the extreme Reissner-Nordström, and you have this series that you write in this one-parameter family of coordinate, leading term Bertotti-Robinson. Here is a linear correction of it, and you start with a solution that is a mu equal to 0 solution. It's a mu equal to 0 anabasis solution, so it solves the linearized Einstein equation for Bertotti-Robinson in Poincare coordinate background. Previously, when I said what is an accidental symmetry, I was saying anything that can solve this equation. So any x's that can solve this equation when applied to this H. Now doing that for NEC is kind of difficult. But what's the intuition? I mean, we know that there are non-trivial solutions to this equation basically because both the extremal and the near extremal black hole had the same Bertotti-Robinson as their near horizon approximation. That was really the key evidence that led to a non-trivial solution to this equation. So let's see if we can arrange for that. So suppose now you think again about doing this linearized diffeo only on the perturbation. So you send H to H plus the derivative of H, and let's say the diffeo is of size mu. What we learned before is that for the accidental symmetry of interest, psi minus 2, this thing that was produced this way could have been thought as a new perturbation around Bertotti-Robinson, which in a series like that builds not extreme Reissner-Nordström anymore, but near extreme Reissner-Nordström. So unlike this guy, little h, which built extreme Reissner-Nordström, this guy builds near extreme Reissner-Nordström. So an idea for a method for finding this psi minus 2 without actually going into solving the Einstein equation is to find a one-parameter family of coordinates that you apply on generic Reissner-Nordström in such a way that then you can expand in the parameter lambda, but also in the deviation from extremality in mu, and have this type of double series expansion of Reissner-Nordström. If you can identify such a coordinate transformation, well then you will be able to identify psi minus 2. Let's see how. Let's see how you do that in practice, let's say for Reissner-Nordström. Starting from the first line, we already showed that this type of series from extreme Reissner-Nordström can be produced from this limit. Now, if you have a near extreme Reisner Nordstrom, let's say of charge to mass ratio of this form, imagine doing a further coordinate transformation, following up that one with this one. So this is now so far an arbitrary coordinate transformation Xi of size kappa squared. If I combine the two, what I mean is that I will do this coordinate transformation on generic Reisner Nordstrom. And then I will expand in lambda, but also in kappa. So what that produces is this series here. So now I have generic Reisner Nordstrom, which I have written in this set of coordinates. Kappa is the thing that parameterizes the difference from the deviation from extremality, but I am expanding in kappa as well. And so I have these 4 terms. Now, if kappa was 0, then that means I'm just in this story. I'm doing the expansion of an exactly extreme Reisner Nordstrom. So obviously I have this series, and therefore this little h here is a linear solution around the background Bertotti-Robinson. But notice that in this series, I can also think of setting lambda equal to 0. And then this guy here is also the first correction of an expansion of a nonlinear solution around another nonlinear solution. So that big G here is also necessarily a solution of the linearized Einstein equation around the same Bertotti-Robinson background, and that's for an arbitrary Xi. This big G and this big H, they come with kappa squared, so they depend on Xi. But for an arbitrary Xi, this big G is always a solution. How about this H? Is that a solution around the background G Bertotti-Robinson? Well, not generically, because now this isn't just a linear correction around the background G Bertotti-Robinson. But we can make it. So suppose we do want this to be true. We do want the H perturbation to be a linear solution around Bertotti-Robinson. One way to achieve that, and the only way here really, is to set this big G equal to 0. So now that gives you equations for the diffie of Xi. If you do this, you will make this series look like that. And if you solve the G equal to 0 equations, you will find that the solutions are these. So precisely the accidental symmetry plus the SL2 generators. All right, so let's recap real quick. What do we have? Initially, we have little h, which is a mu equal to 0 anabasis of Bertotti-Robinson. Little h, mu equal to 0 anabasis of Bertotti-Robinson into extreme Reisner Nordstrom. Now, looking at this line, we have h plus kappa squared big H, a mu positive anabasis, because it's going to build out of Bertotti-Robinson a finite temperature Reisner Nordstrom black hole. Now, does that look like this, the way we defined accidental symmetries originally? It does, provided I can identify big H with a Lie derivative along this specific psi minus 2. Can you do that? I'm not going to go into the details, but yes, you can. You can produce this little h and this big H in any gauge you wish. If you align the gauges appropriately, then you can make sure that this equation looks exactly as before, with this big H now being the Lie derivative of this psi minus 2, along this psi minus 2 of this little h. So that can also be done. For Reisner Nordstrom, it's relatively easy. For NEC, it's uglier. But let's see the derivation of psi minus 2 and look at it also for NEC. How much time we have? 10 minutes, right? Yeah, okay. So NEC. Now, NEC is much complicated. This new method was devised to treat it, actually. So here, why is that? Well, because care is kind of complicated, but here it is in all of its glory. It's a beautiful solution, somewhat more involved, but a very beautiful solution. The extreme care here is obtained by setting the parameter A to M. So this A measures the angular momentum. So maximal spin is A equals to M, and if you do A equals to M, you have extreme care. The way to get NEC out of it is to apply to it this coordinate, one parameter family of coordinate transformations and expand in lambda. So then you have an equation like this, extreme care, NEC plus the first order correction, H. Again, looking for accidental symmetries by actually solving this linearized Einstein equation like this for Xi is tricky. Why? Well, because first of all, in metric formalism, there's no gauge invariant quantity. You might have to go to Newman-Penrose formalism. But most importantly, in this equation, it's hard to ensure that the angular dependence separates from the radial dependence. So if you've ever dealt with the linearized Einstein equation around rotating spacetimes, you know all of these difficulties. So let's use the second method. Let's use the second method. And what does that mean? That means consider generic Kerr, which you know. When you know the entire family of asymptotically flat black holes, the nonlinear solutions, you can use method number 2, the new method. So take this Kerr solution, and imagine that it's not exactly extremal. It's just generic Kerr with this charge to angular momentum to mass ratio, and do this coordinate transformation on it. So take this with A over m equal to that, do this coordinate transformation on it, and expand now again in lambda and kappa. The way to obtain this transformation is, again, start with this one and follow it up by sending t and r to kappa squared corrected versions of themselves. If you do this, you will produce this type of series starting from the nonlinear solution of Kerr. And so now, again, you can ask, are there solutions to this equation g equal to 0? If there are any, then that will be an accidental symmetry. It will produce a new solution that is a linear solution around just neck. And if you do this for Kerr, for neck in this case, you do get, again, a bunch of solutions. What are the bunch of solutions? They are the isometries of neck, which are SL2 cross U1. There's also U1 due to the rotation thing here. But there is yet again a new solution. I'm going to call it psi minus 2 again, and it is written here. So it's basically the same as before, has a d by d phi term here. And again, as before, together with the isometries, with psi 0, 1, and minus 1, they collectively combine very neatly into these vector fields. So once again, if you consider other modes of this, then you are moving off shell. But you might be interested in doing that because these are actually Virasoro generating vectors. They have been previously proposed as asymptotic symmetries of Kerr CFT. Never fully understood, but they have been proposed. And interestingly, there is one interesting difference between the Reisner-Nordstrom story and this story. If you want to make sure that what this produces is something like that, but with this big H now, so the lead derivative of the specific psi minus 2, you need to adjust the gauges, as I said before, for both this little h and this big H. But unlike the Reisner-Nordstrom case, you would only be able to see this equation arising in a gauge that is singular. So that's curious. It's nothing to worry about, because if you don't go to those singular gauges, all of your perturbations, all of your vector fields are perfectly regular. But if you want to display this equation, you only can do that in singular gauge choices. OK, that's not the first time it appeared in perturbative problems of neck. It's curious. One might wish to think more about it. All right, so I have a few minutes, so let me summarize real quick. What are accidental symmetries? Accidental symmetries are coordinate transformations which act on perturbative solutions of the linearized Einstein equation around extreme and near extreme black hole horizons. And what they do is they map perturbative solutions amongst themselves. We saw that for the story Bertotti-Robinson to Reisner-Nordstrom, what they do within spherical symmetries, there is one such accidental symmetry. What it does is it turns on deviation from extremality. Start from exactly extremal one, you turn on deviation from extremality. For neck, similarly, this psi minus 2 I just showed for neck is doing a similar thing. It can start with neck plus a perturbation that's going to give exactly extreme Kerr, and it then produce a perturbation that's going to start from neck and produce near extreme Kerr. In both cases, that psi minus 2 combines neatly with the background isometries, the SL2s, into a Virasoro algebra. And in both cases, it can be thought of as a non-shell version of a large diffu, of an asymptotic symmetry of those asymptotically ADS2 solutions. Now, what's more than that is that we saw, even within spherical symmetries, that I can use accidental symmetries beyond this type of addition of charges, but I can use accidental symmetries to turn on dynamics as well, turn on propagating waves. The way we did it for Reisner-Nordstrom is we added scalar waves in spherical symmetry, and we turned them on with certain vector fields. Now, what are we doing now? We're doing the same thing now for gravitational waves of neck. This calculation for scalar waves of Reisner-Nordstrom is proxy for the axisymmetric gravitational waves of neck. And so we expect, this is still work in progress, of course, but we still expect that it should be possible to turn on gravitational waves that are axisymmetric around neck by acting on the analysis solutions of of neck with some appropriately chosen differ. All right, this is the end, and I'm happy to take questions.